Okay, a warm welcome to all of you to our meetup. This monthly meetup happens every last Wednesday of the month. This time we actually had to move things around because of some scheduling conflicts. My name is Jules Damji. I'm going to be your host today. Joining with me is our Ray Serve team, Edward Oakes, Simon Ho, Zhao Dong, and Shreyas Krishna Swami. You guys want to say hello to the community?
Hey everyone, thanks for joining.
Thanks for joining. Anyway, we got a big agenda today, so we're going to get actually started. Thanks a lot for really taking the time to join us. As you know, community is the center of any open source project, and you guys are being part of it. Taking the time to join us is quite important for us, and we really value your not only your contribution but also your participation. And so, if you would like to give a talk here at the meetup, whether it's a lightning talk or a general 30-minute talk about your journey with Ray or any of the libraries that you actually use to do your machine learning workloads, we are very much interested to hear about it. So do let us know. Send me an email at jules@anyscale.com, and we'll try to figure out a way to put you in. We accept lightning talks. It's actually a great way to have that. So let us know if you're actually interested to do that. Now, here's the agenda for today. No meetup is complete without any announcements. I'll have some announcements before we actually head out. We have a great series of talks today. We're going to start with Edward Oakes, who's the project lead for Ray Serve, along with Simon Moore, who's going to be sitting in the background answering all your technical questions while Simon is giving us an overview and a roadmap to set the context of what the next two talks are going to be, followed by Zhao, who's going to share with us how do you actually build, multi-node inference graphs, and how do you actually scale it, and why it is so easy to use the Pythonic APIs to be able to actually build your direct X-linked graphs you can actually deploy quite easily. And then we'll have Shreyas, who's going to sort of tie up things. How do you actually operationalize something that you actually have in your deployments at scale, and how do you actually manage that through these very operational friendly APIs that we have coming up in our recent release and a couple of series down the road. And then finally, we'll actually have a demo that actually ties up everything that you hear from Edward, Zhao, and the team. So hang around for the finale demo. A couple of announcements we actually have. We are having our first in-person Ray Summit sometime late in the August, in 23rd and 24th. We're still accepting papers. They're going to be closing on April the 18th. So you still have time to submit those papers. Forget about doing your taxes. Just go ahead and submit your CFPs. I'm looking forward to read your submissions. So do that. And then obviously the Ray Summit is coming up in August. Submission registration is up for open. We're going to be putting in our keynote speakers and agenda coming up very soon. There's an early bird registration process. Do feel free to peruse through it, and we'll be putting more content about what trainings we are doing. So do come and join us in the late summer. And then finally, as I say, and I keep on repeating every time when I go to a meetup or every time I give a talk at a conference, is that community is really a center and at the core of any open source project, and your participation in contributing anything that you actually feel that you think should be part of a Ray ecosystem, please file an issue on GitHub, or if you're willing to contribute, please do that on the GitHub. We have a very lively and vivid discussions happening on Discuss Forum and Slack, where we have all the committers and all the authors and the communities discussing about technical issues with Ray. So do join us if you want to find out and keep abreast with what's happening with Ray. We have a monthly newsletter, and obviously I live on Twitter. So if you actually want to find out anything and everything about Ray, what people are doing, how they're actually using it, what use cases they're using, follow us on Twitter and join us in the community. Now, with that said, I'm going to now sort of hand it over to Edward, who's going to sort of give us an overview to set the context for the rest of the talks. Edward, all yours.
Thanks, Jules. Okay, so you should just be seeing my slides right now. Is that right?
Yep.
Okay. All right. Thanks so much, Jules. Yeah, so my name's Edward Oakes. Like Jules mentioned, I am a software engineer at Anyscale, where I lead the Ray Serve team. So today I'll be giving kind of a gentle introduction into what Ray Serve is, what we're seeing people use it for in the wild, and then talk a little bit about some of the current developments, as well as what we're working on looking towards Ray 2.0, which is going to come out later this year. And a lot of these things that I'm talking about will be covered in the next two talks by Zhao and Simon, and they'll go into a little bit more detail. So let's get started. Okay, so outline of the talk. So I'm going to start with a quick introduction of Ray Serve. Then I'll go into what we've been hearing from our users. We do events like this Meetup all the time. We're really active on Slack, and we love hearing from our users about what they love about Ray Serve and also what's missing. So I'm going to go over some of the trends that we've heard there. And then I'll talk about how we're taking that feedback and improving things for Ray 2.0, as well as a little bit about the extended roadmap. And like I said, this will be a preview for the talks that you'll hear later today. So before we dive into Ray Serve, let's talk a little bit about the Ray ecosystem. So Ray is a universal framework for distributed computing. It offers a simple but powerful API for building distributed applications and is especially useful for distributed machine learning applications. It can run on top of all the major cloud providers, as well as Kubernetes or in on-prem clusters. And it has a wide ecosystem of libraries built on top of it that allow you to really build incredibly powerful distributed applications. So some of these libraries you might be familiar with, like Dask or Mars or Hugging Face. And there are also some native libraries such as RayTune and RLib. Ray Serve is one of these native libraries that is a compute layer for model serving. So let's go into a TLDR of Ray Serve. So Ray Serve is a flexible, scalable compute layer for model serving. It's built on top of Ray, like I just mentioned, which means that it inherits a lot of really great benefits. It's scalable. You can build low latency serving applications, and it's also efficient, which is really important in machine learning inference, where you may be running workloads 24/7 and compute can be really expensive. It also has first-class support for multi-model serving. I'll talk more about multi-model serving in a minute, but this is a trend where we see more and more machine learning applications require more than just a single machine learning model to work end-to-end. And finally, Ray Serve is Python native, and it allows you to easily mix business logic with your machine learning models to build like end-to-end machine learning applications. So let's dive a little bit deeper into what I mean by multi-model serving. So we're seeing this pattern, especially when talking to our users, that oftentimes building a machine learning model is not just training one classifier or training one regression model and then sending requests to it and getting an output. Instead, if you're building something for a real world workload, you often have to combine multiple models, even for just a single request. So let's dive into an example of this. So imagine that we have an application where we want to synthesize a description for an image. So we can't just train one basic model in order to perform this complex task. Instead, we have an image processing pipeline. So in this example, we first need to do some kind of pre-processing on the image. So maybe decode it and do some basic pre-processing like augment it or clip the image. Then we might have a classifier followed by something like key point detection. And then finally, if we want to synthesize a description, we need to use some kind of NLP model. So this is much more complex than just having a single trained machine learning model. And also note that all of these models may have different resource requirements. The pre-processing step might be pretty lightweight and run on CPUs, while the NLP model might be a heavyweight deep learning model. And we want to be able to run this efficiently and scale it up to many requests. So I just described sort of a pipeline multi-model inference application, but this is just one of the types of multi-model serving patterns that we see. We also often see ensembling, where for a single request, you may fan out to many different models and then only return one of the outputs or maybe combine the outputs. And we also often see machine learning models mixed with business logic. So you may make a request to a model. Based on the response, you may select one or more downstream models. So a common application here might be for something like fraud detection, where you need to mix hand-tuned rules with machine learning. And Ray Serve is a really powerful tool for building these types of multi-model serving applications. So it allows you to define this entire distributed inference graph as a single unified Python program. You can continue to use your favorite tools and libraries. For instance, you might use PyTorch for the actual, for one of your models, and you might want to use like an off-the-face, Hugging Face model for another. And it also allows you to scale out across CPUs and GPUs, and inherits Ray's flexible scheduling so that you can do this efficiently. So now that I gave a quick intro of Ray Serve and the applications that we're seeing it used for, let me dive in a little bit into what we've heard from the community. So as I just described, we're seeing more and more that people need to do this type of multi-model serving. So this is a really big need, and it's also something that Ray Serve is really well tuned to. But while the Python API is great and people are seeing a lot of success building their applications, we're still seeing some friction when people want to go to production and have a automated workflow such as CI/CD for deploying and updating their models. One of the emerging patterns that we're seeing is continual learning, where people want to retrain their model weights very frequently in order to ensure that they're providing the best outputs. And many times this would be like recommendations. They're providing the best recommendations to their users. And while there are users that are successful doing this today with Ray Serve, we want to make it as easy as possible so that you can really just focus on the application logic. And finally, a constant thread is that machine learning inference is really expensive. A lot of these models are compute intensive, and oftentimes you want to run on expensive hardware like GPUs. So efficiency is always key, and we're always looking for ways to make it easier for our users to have cost savings. So given those takeaways that we have from talking with our users and seeing posts on the forum and Slack, so let me talk a little bit about what we're working on for Ray 2.0. So the first thing is we're doubling down on this multi-model serving use case with a first-class API called the Deployment Graph API. You'll hear about this from Jiao later today, but this gives you a really flexible, powerful API that can be used to write high-performance multi-model serving applications. We're also investing in improving our support for automation and deployments. So we're working on a structured REST API and using that to improve the Kubernetes support. And you'll hear more about this from Shreyas in the talk later today. And we're also looking to integrate with a lot of the best in breed MLOps tools. There's a huge ecosystem of really amazing tools for things like model versioning and saving model artifacts, such as weights and biases and ML flow, as well as monitoring things in production and doing model drift detection, like Arise and YLabs. And we're not really trying to reinvent this ourselves, but we want to make it possible to integrate with the best possible tools using Ray Serve and make that as seamless as possible. And finally, earlier I talked about the Ray ecosystem. And one of the things that we're really trying to do across all of the Ray libraries is to improve interoperability. We want to make it completely seamless to go through the entire machine learning lifecycle, from data processing to training, all the way to serving in production. So there's an effort for Ray 2.0 called Ray Air, where we're trying to make all of the native libraries really interoperate as easily as possible. So in addition to the things that we have in progress for Ray 2.0, we also have a huge backlog of items that we've heard from our users. These are things like scale to zero, or supporting gRPC, or supporting many, many small models on a small amount of hardware. And as you might have seen in this talk, where I first talked about what we're hearing from the community, and then you can see how that directly maps onto what we're currently working for Ray 2.0. So here, I really want to encourage everyone to please get in touch with us. We really want to hear from you, because the only way that we know what to build in order to make your lives easier and enable you to build really, really cool, powerful applications is if we get that feedback and we hear about your use cases. So please get in touch. There's a lot of ways that you can do this. You can join the community and talk to us at the Discuss forum at discuss.ray.io. You can always file an issue or leave a comment on GitHub, or get in touch on Twitter at Ray Distributed or Anyscale Compute. And we also have this survey at the QR code below, and I'll leave the screen up for a while so that you can scan it. And if you fill this out, it'll make it really easy for us to get in touch with you. And we're happy to set up one-on-one sessions with the Ray Serve developers, or to keep you updated about any of these features that we talked about today, or about the extended roadmap. So that concludes my talk. And yeah, I think we'll move on to Q&A now.
Edward, thanks a lot for that wonderful introduction. I think this is actually quite important. What you actually brought up on the screen is because, as I said earlier, community is at the core and the center of any open source project, and having all these people actually participate and give us constant feedback is how we actually improve, both critical as well as constructive feedback. I think collectively we can actually make that a lot easier, as I believe that innovation doesn't happen in isolation, it happens in cooperation. So this is actually a good way to move actually forward. So do please fill up this particular survey and get in touch with us, and we'd like to talk to you. Now, I'm looking at some Q&A panel. A couple of questions that I have, Ed, for you. You mentioned something about scaling to zero. Could you actually elaborate? What does that actually mean, scale to zero? I always hear about scale from 1 to X or 1 to infinity, but what does scale to zero mean? Can you talk about that in terms of what does that mean with Ray Serve?
Yeah, absolutely. So this has been something that we're starting to hear somewhat frequently from users, where they may have many, many different models. You can imagine a scenario where you're doing something like product recommendations, and you have 1,000 product lines, or 10,000 product lines, and you have a request come in, but it may only actually hit a small fraction of those. So you only want to have the models that are currently being used actually loaded into memory and consuming resources. So if you have just a few products that are really, really popular, and you have a long tail of other ones that don't get requested very often, people want scale to zero, meaning you can scale down to not consume any resources while those less popular ones aren't being requested.
So scaling down to zero would be as if you're having a cold standby alarm, and if you actually need that, then you can just scale up. Is that
Yeah,
metaphorically or euphemistically translate to that?
Yeah, that's exactly right.
Okay. The other question I had that popped into my mind, it's not actually from the community, but this is when you were going through, you did mention that you are listening to the community, and some of the things that you found out that people build all these different models in production. They have composite, they have ensemble, they have business logic, they have pipeline. Where did you find out most of the common scenario? In other words, of the 5 deployment patterns that you see, which was the most common one that you actually felt that you heard invariably? Was it ensemble? Was it composite? Was it only business logic? Where did you feel that most people are using it?
So I think honestly, one of the important things here is that every business application is a little bit different. So we do see a wide range of things here, and that's why it's really important that Ray Serve has this very flexible API that you can kind of tailor to your needs. Mm-hmm. But I would say there are a few sort of common patterns that we see. So for instance, with recommendation models, you often see like an ensemble approach where you have multiple models and then you combine the outputs. And for image processing, it's really common to see this type of pipeline, sort of like the example that I gave earlier, where you first feed the image into one model and then to another and another and another. So I would say that they're all pretty common, but we see kind of like clusterings in different application areas.
Okay, I have a question from the community here from Zach Werner. Are there ways to hack around lack of scale to zero support in Ray Serve today? Are there ways to hack around lack of scale to zero support in Serve today? In other words, we don't have that. How would you hack around that? If we are not using Ray Serve today, have rolled our own versions of LRU cache because we have thousands of models that we have to serve, and we don't want to store them all in memory. So
I can answer that. So yeah, you definitely could hack around not having scale to zero support today. So yeah, you should definitely get in touch, by the way, on the survey or on Slack, and we can discuss this in more detail. But using the existing Python API, you could definitely implement scale to zero yourself with just kind of a lightweight coordinator actor or something like that. So yeah, this is definitely possible. It just doesn't sort of work out of the box. But yeah, would love to get in touch and discuss how we can make that work for you.
Thanks a lot, Zach. Do please send us join our Slack channel and do ping Edward, and we can actually have this conversation offline. I think it's an important thing because I think it might be a little while before we actually have that roadmap. But having a temporary solution would be great. James Liu actually has a question. Could you elaborate on how you approach the continuous learning? What is the pipeline looks like? In other words, somebody who wants to do continuous learning by they find a model that needs to be fed back into CI/CD to train again, then redeploy it. Could you explain what that means?
Yeah, absolutely. So I would say that the most frequent way that we see this working is basically, people are serving a model, and then right now I would say like they have a periodic, just sort of like cron job that will trigger retraining the model on the most recent data. And then you'll have some kind of like, just like batch inference evaluation to test that model is performing well. And then you actually, and that all happens sort of outside of Ray Serve. And then when you go to deploy it in Ray Serve, oftentimes these happen very frequently. So people will use the dynamic update support in Ray Serve to just apply the new model weights. And that will trigger a pretty lightweight, like rolling update in Ray Serve, and like re-download the model and just start serving the new one.
Okay.
So the way that you actually,
go ahead.
Oh yeah, I was just going to say the way that you actually sort of apply the new model weights is requires a little bit of like manual implementation today. And Shreyas is going to talk about that in his talk, how that could be improved.
Okay, we're going to take one more question, and then I'll have Simon answer the other questions by typing the answer from Osama as well, as we actually have to go on to the next one. Can runtime environments be used to compose multiple models, which might have conflicting dependency into a single pipeline on a single Ray cluster? That's an interesting one.
Yeah. Yes, that absolutely can be used. So you can specify a runtime environment for a given like serve deployment. And these could have conflicting dependencies. You do have to be a little careful that you're not exchanging objects that, if you use two versions of PyTorch and you pass like a PyTorch object between them, that might cause problems. But if you're just passing normal Python data types, then there's no issue.
Brilliant. I think we'll end that with that, but we can actually take some of the question and answer since all of us are here online by typing the answers so everybody can actually see. So Edward, thanks a lot for that wonderful insight and giving us a roadmap and setting the context for the next two talks now. Zhao, we actually have you as our next talk to tell us, how do you build graph APIs and what's so great about it? So please let us know.
Hey, can I see my slides right now?
Yes, we can.
Okay, let me hit some controls. All right, so thank you, Jules and Edward, for the introduction of Ray Serve in general. And this is Zhao, an engineer at Anyscale working on open source Ray Serve. I'm here to give you more overview and a deep dive into the Serve deployment graph. And in this talk, we're going to cover a few topics. And the outline is we're going to show you some motivations we had in mind and learning from the community and the industry why we think multi-model inference graph is an important pattern we need to support. We'll walk through some context of Ray and Ray Serve and why Ray and Ray Serve is really well suited to solve this type of problems. And then we will give a very comprehensive API walkthrough to show you a demo simple example end to end with all the APIs and details covered and show you an example how you build one end to end. And we also have a documentation in our website for all the details included. At the very end of this meetup, we're also going to have a real live demo to have a real content understanding pipeline build. We're going to show entire life cycle of authoring, deploying, and iterating on the inference graph. Okay, so let's get started with motivation. So machine learning inference graphs are getting longer, wider, and more dynamic. And this is an important pattern and trend we noticed by talking with users and learning from the industry. And by seeing longer, as previous Edward also showed, you often have multiple models form a natural chain of actions for the final prediction. And they have a strict dependency. And the more models you have, the longer the chain would be. That's what I mean by longer. And by saying wider is usually for some particular decision-making patterns, for example, a content understanding of a computer vision model, we often see people need to send the same image to a collection of models in parallel. And the magnitude could be 10 or maybe 50 of those models collectively. And ensampling going to happen at the end to aggregate the results. So that's what I mean by wider. And also, it's getting more dynamic. We often see people need to mix business logic and dynamic dispatching pattern into this complex inference graph. For example, what I show at the very right-hand side, we have a dynamic selection that we will dynamically decide to route the request to a particular subset of models if I know something about the attribute of my input, if it's a cat or if it's a dog, right? And also, we often see people need to continuously do lightweight updates for their existing deployments to make it easier to configure and without changing out the entire cluster. So you can see more details about one of the blocks we have to capture the patterns of ML models in production. Okay, and now in this slide, we're going to walk over the unique strengths of Ray. So Ray is really powerful at writing simple Python applications, but also make it very scalable. It's also low latency. In the particular scenario, we're going to walk through more details about why we have advantages of building low latency and more efficient multi-model inference graph. And also, we double down on the interop between different libraries of the Ray ecosystem as the compute substrate of an ML platform. So if you use your application of retune, rechain, using Ray Serve, we want to provide an end-to-end seamless experience, so whole piece is connected. So let's start with one example of what the existing API we have and how Serve works in a little bit more detail and leads to a single deployment experience, as well as how that leads to multiple deployment graphs. So in our existing API, you can start with a model class, and that could be a class or function, and let's call it model, which is a simple Python implementation. And then we can add a decorator to it. We call that serve.deployment. And we can deploy this class directly. Let's call it my model.deploy. And by default, we got two things, all of it, exposed to you as a user. We have an HTTP endpoint. And in this case, I'd say if you're doing local testing, we expose a local host endpoint, and you can hit it with your HTTP data. In the meantime, we also expose a Python handle. And the Python handle means you can grab this handle to correspond to my model deployment and just calling .remote and send your user request to it. And we found this by design. We want to facilitate multi-model composition, so you can use a Python handle, essentially program your deployments and program the inference graph. So this is a primary tool people are using nowadays to orchestrate and build their multi-model inference. Now let's walk through one example. And this slightly get more complicated, but it's a very common pattern we observe in the industry. So at the left-hand side, you can see we have an input image, and we want to go through some pre-processing. Let's say we normalize it, we crop it, and reshape it, resize it. And after pre-processing, we dispatch this into 3 different classification models or object detection models in parallel. And I want to aggregate them, the results at the end through a combiner, and then do the post-processing or aggregation at the end. Now, on the right-hand side, you can see this is a code snippet of the implementation we see our users are doing using the existing API. So you can see in the constructor, we need to explicitly pass in a bunch of models and essentially the deployments. And in the constructor, we need to get handle for each one of them and hold a reference to it. And there are a few problems with noses with this pattern. And so at least one of the attributes you can observe here is when you're looking at the classes and you assuming your inference graph got really large and very complicated, the dependency between different nodes in the graph, in this case, the different classes, is hidden from you. And also in here, a user needs to explicitly call and get handle every single time for the model and deployment they want to use. And also when user needs to call into those models, when you send a request, and you can see people need to manually orchestrate this communication and essentially they need to be familiar with Ray APIs, also need to use it correctly in order to not lose performance. And here, actually, you can see this is one of the anti-patterns that we discourage users to do because this person is doing a wait in for loop, which we rather have this object refs called in a batch, so it's better vectorized. So it's also hard to write efficient graph. Technically, this code snippet runs, but we can see a few patterns we noticed from this case, even though it's a really simple one, and that will be making it hard to scale and enable users to write more complicated applications. So To summarize, those are the challenges observed with menu composition. So the deployment graph topology is hidden. So there's no single place or easy way that you can know what my graph look like, what my competition graph look like without reading through the code line by line, model by model, class by class. And this can make it very challenging for operationalizing. For example, let's say if you're trying to deploy a model, and you will need to know which order you need to deploy each model with respect to the correct dependency. That's one. And also without a static definition of your deployment graph, it'll be really difficult for an ops team, which we can assume we have a data science team. So we have an ops team who's responsible for operationalizing this deployment graph, to know what is going on. They require deep understanding of the code base. And the third issue we observed in the previous code snippet is it's also really hard to write efficient graph where everything is resolved at runtime with no high-level static definition. It also eliminates the chance opportunities we can provide to users because some of the computation patterns we can easily auto-tune, co-locate, and optimize by putting different models and different nodes in the same physical machine, in the same container, or even within the same process. So therefore, we observe those problems and we want to bring a solution to you is we need to introduce a graph building API. And to walk you through the solution we have in mind and a few design principles and considerations we have in mind while designing this API. So first of all, we take it very seriously about this API to be Python native, which means we want to make it fully Python programmable as much as possible, without a need of writing a YAML file to begin with. So while we're researching existing solutions in open source, we find that one common pattern is the very first thing that people ask you to do if you want to orchestrate and author a deployment pipeline is you need to learn their YAML format, you need to learn their schema, and you need to write a YAML file with manual handwritten dependency between them. And we found this experience less desirable, and we want to bring Python as a first-class programming language. And we are biased towards in saying YAML itself is not a Turing complete, and it is not a programming language that user wants to use at the authoring time at least. But in the meantime, we think YAML file is also very valuable, and is industry best practice also use YAML or YAML file equivalent, because it's very easy to, for operations, it's very easy to operate and understand your deployment graph in a single file, YAML file, that you know exactly what is going on, what configuration you have used, how it's deployed, how many replicas you have, and then you can easily turn the knobs to reconfigure lightweight without understanding code. We also highly value this pattern. So we're not eliminating YAML, and in our end-to-end solution, we actually have a YAML file for the configuration as well, because we think this is the right contract to use. But our argument here is we can have the benefit of both. We can have a fully Python programmable way to author your graph without writing YAML for the data science team, MLEs, or at authoring time for your iteration. In the meantime, we can automatically generate the YAML file for you, so you can later use for deployment and reconfiguration. And the second point is, given we highly value local development experience, we want to bring the best experience to you and in Pythonic way. So which means by design, we want to make sure all the authoring iterations you can do can be developed, instantiated, tested locally on your laptop. And in the meantime, in inference graph scenario, it's very easy to see when we have multiple models combined, they have different hardware resource requirements, they have very different compute patterns. Some of them could be CPU intensive, some of them might be memory intensive. And we take it very seriously about leveraging the strengths of Ray, which we showed earlier, to make each model and each node in the deployment graph independently scalable and configurable. And we also use this as a unified graph API because we acknowledge the fact that DAG is a very common, and graph is a very common abstraction people like to use. And you see this in inference graph, this is in machine learning models, you see this in data pipelines. So we want to make sure the API we introduce is unified across the entire Ray ecosystem. Okay, now I'm going to walk you through one example we have in the documentation, which you can check out on our website. And please have full attention here because this might be some details here that you might get lost. And I will try my best to cover everything we need. But we have 5 steps here. And it's important I have a high-level overview to show you what the application is about, and I'm going to walk through each step later on. So let's say I start with a single node that captures your input to this graph. And it could be any Python object, maybe an image, maybe a text, maybe a paragraph, maybe a list of numbers. And for the same input, I want to send to two preprocessors. And the preprocessor here could be a class or a function. And for the example, let's say for simplicity, let's use a function. And the same request that you send in will be fan out and dispatched to those preprocessors at the same time in parallel. Now, after the preprocessor finishes the computation, we're going to have a combiner to combine those outputs as a single request. And the single request then will be dispatched to two downstream models. And we can assume those to be a model to do some recommendation or computer vision or natural language processing regression model. And at the very end, we're going to have an aggregation to aggregate the results. And I added one more arrow here to flip from your input to the final stage of dynamic aggregate. This means this final aggregation not just takes the output of model 1 and 2, which is my directly adjacent neighbor, but I can also come from arbitrarily random upstream nodes. In this case, it's directly your input. In your input, we configure, actually, I want to take the sum of the output of those two models, or I may want to take the average, or I want to take the max value of them, depending on what I want to do for this particular request. So this shows about control flow and dynamic aggregation. Okay, so let's get started with the first step. And so your input is here, and we introduce one of the key API here is we have a class called input node that represents your input to the graph. And this object will be resolved at runtime. And the context we use here is you can use a with input node as a context manager and simply assign a name to it as DAG input. This DAG input is a global singleton with respect to a particular graph, because at each time your invocation of your graph, we assume you only have one input, even though the input could be a complicated object. Now let's send it to the preprocessor. And here we're going to have the second API we introduced, .bind. And bind is our first class graph building API that could work on any supported decorated class or function. And what it means here is for this particular preprocessor, let's say it's a function decorated by serve.deployment, we can directly call in .bind. And the inputs we feed into it is the partial value of your usual input at index 0. And as a result, we created a node in this graph. And that input node is also another node in this graph. And they're connected. They're connected because we claimed the preprocessor need to take parts of the original first input. And we can assign a variable to it called preprocess1. Similarly, we can also do that for another preprocessor. Let's say we call this and taking average of your input. And we can use the same context calling .bind, but then we can take your user input at index 1 and bind it to the average processor function. And we assign a name to it called preprocess2. And we aim to make this as intuitive as if you're writing plain Python code as much as possible. And the only new concept in here is essentially the .bind. You're calling .bind to bind the futures for the future inputs you're going to receive at the runtime. And yet we have a static definition of the dependency. Now, the second step here, now we have the input to the graph. And let's start adding models. So .bind can also be called on a class or a class method. So what I mean here is, let's say we have a model class decorated by serve.deployment, and its function signature, essentially, I can instantiate this model class with the initial value that represents my weight. It's just an integer. And in this case, calling model.bind1 means I want to get an instance of model, initializes value of 1, and I want to use it later on. So I assign a variable named m1 to it. Similarly, I can do the same for another model. And note that in this case, the model implementation is exactly the same. And we can reuse the same class definition and give a different instantial value input argument to it. And now let's start combining. Our combiner have a dependency for M1 and M2 because it needs to take actions on those two models and to dispatch a request to. So a combiner, if we check the signature of the combiner, could simply be, I need to have two classes that I can take action on. And I want this in my constructor. So essentially in here, the combiner.bind M1, M2 means I can use those two models into combiner's implementation. So in here, you can notice, even though we are creating nodes as intermediate values as we're building this graph, we can pass around nodes as input arguments into other parts of the graph, either as a part of constructor or as a part of function call. And now let's connect this with the previous parts we have for your inputs going through two preprocessors and combining here. And now we have another bind on a class method. Our implementation of the combiner can have a user-provided implementation, say, just called .run. And the .run, when it's executed, it will take some actions on the preprocessed value upon evoking the model 1 and 2. But I can use the previously computed values, which I call preprocessed 1 and 2, the values I have computed previously. I can directly pass this in, assuming they'll be resolved at the runtime, as well as a user original input telling me if I want to do a sum or I want to take a max. So this is a valid DAG. We can run it end to end. Essentially, this means we have the preprocessed input assigned to a combiner, and combiner will take the instantiate models, and depending on the user input we put, it will call its run method. Now, the third step is the last piece for this DAG building, which is about dynamic aggregation. And as mentioned earlier, we have three arrows pointed out here. Let's say we have one model 1 output. I just use a color to represent this particular variable. And model 2 has its own output too. And also user input is a particular operation I want to tell what to do. So let's have a dynamic aggregation here. It could be any function or a particular class method within the class implementation, up to your choice. And all we need to care about in this case is how we bind it. And you can see dynamic aggregation could be done very trivially, even though the dependency could be complicated, because we literally just make it as if you're writing a Python application. You pass those values in, which are available upstream in the previous DAG building. And upon receiving it, in your implementation of this dynamic aggregate function, you just simply write Python code. If the operation I got is a sum, do sum. I mean, if the other one I get, I just take a max. So this essentially concludes the backbone building of this entire deployment graph. Now, let's step into the Ray Serve territory, because now we need to expose HTTP and we need to configure other attributes that are serve specific. So let's start with the DAG we have in here already. And this we call this a unit of DAG. Now, we need to have one more deployment that exposes HTTP and it is a user-facing component. And a lot of things can happen in here. You can have fast API integration. You can have HTTP endpoints. You can have other things that you care about for particular exposing this particular graph. And driver is also a deployment. So all the nodes you see in here is a serve deployment, and the driver is no difference. So when we bring the driver, we provide a default driver implementation that you can directly import. But if you need to customize, you can also feel free to implement your own, which is also very simple, as if writing a simple deployment class. And now you can bring your own options for this DAG driver. And in this case, I'd say I just want to customize the route prefix I want to use for my HTTP endpoint. You can easily just do the options and bring it here. And this I need to bind this driver as the ingress of my application. So I need to call in another .bind to show those pieces are connected. And I need to wrap my DAG into it as well. And we added one more piece for user convenience, also to improve interop between ML libraries in the Ray ecosystem, which we provide a few default input schema adapters. And you also feel free to implement your own. So what it means is, when you receive the request from HTTP endpoint, which we can assume this is a play JSON object. But in an actual DAG execution, you probably want to have another Python object in a more particular structure, particular format or dimension. So we provide a few default ones for convenience. You can also bring your own. And essentially, those two are equivalent. When the driver exposed here will provide a best experience that we can aim, also with the flexibility in mind, so that when you're calling the DAG application you locally tested earlier, and you have the correct Python object to invoke and call into this DAG that essentially got fulfilled at runtime that represents your user input. So this concludes the pieces of DAG building, iterative, as well as exposing the server-specific deployments and HTTP. And the last step is just locally running and testing. And the more concrete details of this is at the end at the end of this meetup, which we have an end-to-end demo. But in here, we can show you a high-level experience of the flow look like. And everything up to step 3, and it's about local developing. We want you to have a really smooth Pythonic local development experience. You can have quick updates, fewer replicas locally tested in Python. Then later on, which is the talk that Shreyas is going to cover more with more comprehensive overview as well as details, is about how we operationalizing this application that you're happy with on your laptop. That includes structured deployments, deployment artifacts, and in the real deployment situation, how you configure replicas you want to use, what a YAML file is going to look like. So seamlessly, we want to have experience from laptop to remote cluster for deployment. And there are a few improvements areas we can do, given that we recently announced this. So one of the key things is about really make it polished for this path from your laptop to remote cluster, which means you improve operationalizing story and how we can not facilitate just the data science team, but also the MLE team and the operationalizing DevOps, MLOps team, which you can learn more from Shreyas' talk later on. And given the fact that we now have a static definition of the competition graph, and there are a few low-hanging fruits we can grab that we can, based on profiling of a deployment graph, because now it runs in the same Ray cluster, we can do some automatic performance optimizations regarding placements, collocation, multiplexing, and better leverage shared memory. And obviously, there are a lot more work we can do about UX and visualization. Ideally, when you deploy your deployment graph, we can have some simple API or simple experience for you so you can visualize what it looks like end to end, what the interface between those things look like. Maybe even later on, if we have enough resource, we can even have a drag and drop, which I heard from some users in particular like this experience to build a deployment graph. Okay, so as a bonus point, I'm going to run through this very quickly. It's just saying DAG and graph is a very common pattern in many competition workload you carry out. Data pipelines, inference graphs, workflows, right? So you can learn more details about this in our public RFC for RAID 2.0. But what we showed you here is essentially completely unified with a common DAG API as a first class in RAID 2.0, which means we have the same set of APIs for authoring and executing, and we have each library-specific piece that fit in well together. Cool. So in conclusion, and essentially I walked you through about the problem we observe in the industry, and we think this is increasingly important problem for us to solve, and Ray is well positioned to solve it. And it's hard to author and iterate locally, and there's a lot of churns, how to deploy and locally test your application, even though it's very complicated, and how to avoid churns of writing YAML files and play around with those YAML files to be more Pythonic. And in multi-deployment graph scenario, we also think performance is super critical because there's a lot of opportunities that user can leverage, and the missed opportunities that could be performed better. That is, simple application is easy to see, but when the graph got larger across the boundaries, it will be more difficult to spot. And in here, we also presented the solution about Serve deployment graph API. And at the authoring time, we really make it Python native as much as we can, and enables your full local Python local development and testing experience. And then we also showed you the path to leverage the core strengths of Ray about making it more efficient and scalable in production. Cool. And this concludes my presentation. And here's the Q&A section. And please get in touch with us, and you can see a few links that if you want to get engaged. Thank you.
Thank you, Gerald. Thank you for that insightful commentary and great talk about the graph APIs. I think one of the things I really liked about the fact that you can actually just pretty much use Python to bind everything together. One thing I wasn't sure about was that I didn't see any specific call to deployment. Where does all the deployments happen for each and every deployment node that you actually have? Is that in the last call where the driver does that, or that's somehow hidden when you do the bind? Could you explain how that happens? Okay,
so about the deployment. So I can walk a little more detail about what the deployment is and how it operates. So a deployment, we can think of a deployment essentially as a group of actors. Mm-hmm. And I'd say it could be holding your application, you might have 10 actors, right? And every single piece you see in our graph building, let's say our preprocessor, the preprocessor by default will make it a deployment. And that deployment could have an arbitrary number of replicas. It could have maybe 2, maybe 5, depends on how scalable we want to make if we observe this to be at a bottleneck. So essentially, you can see the backbone of the deployment graph are backed by deployments. And essentially, there's a little abstraction of nodes drawing circles are backed by individual actors. And that is independently scalable. And driver is also a deployment. So you essentially, under the hood, when we're authoring this graph, we're using deployment as a higher level abstraction. And when the deployment graph is invoked or called into, essentially is just Ray actor calls under the hood. Like we are routing the request to the correct deployment, and then we route it to the next node. In the next node, we're going to find the right replica to serve for the right particular actor to serve the request. And also by knowing the whole dependency graph, we can fulfill up to the end and give you the final result.
Yeah, I mean, I do like the before and after contrast when people were manually composing all those nodes and then actually individually deploying each and every instance of the model deployment. Whereas over here, everything is actually done implicitly and it's very clean. I think one question that pops into mind with this new development graph APIs, what kind of applications would people build using this particular API? That's the first question. And I think the corollary of that question is, what are some of the new possibilities that unfold from this new API that we have unfolded in the Ray Serve?
Okay, and I think for the first part of the question, then we can think of a few patterns where we can assume the node, the model fit in the single node, fit on a single machine, right? So in this, some of the applications, and we learn from the industry, I can give a few examples. One of them is content understanding, image classification. We actually, the end-to-end demo we have at the very end is exactly built for this purpose. Okay. So for some product, you might have a product image that needs to go through a magnitude of maybe 10 to 50 models, and each of them is fine-tuned for a particular purpose. Maybe a model is fine-tuned to learn if this is a bag or not. Maybe the other model is about to learn if user uploaded this image, is that image violent or not? And is this hateful, or is this integrity, like integrity checks, right? And some of this could be about just like, so this image is one particular example. Essentially, we're using the power of machine learning, multi-model collectively to annotate this image so we know more about this image. We can empower other products down the line as they output to other teams. That is one. And the other we can think of is same for NLP, like natural language understanding is the same. Then you can send a document to a particular service, and you want to run through multiple models. Some of the models are good at detecting the boundary of different paragraphs. Some of the models are really good at detecting the boundary of sentences. And some of the parts of the model is good at tokenizing the sentence into a sequence of inputs and getting output. And some of them is good at aggregation. Right? And another pattern I can think of is recommendation system. In recommendation system, it's very common not just mixing multiple model or mixing business logic. You usually have a funnel of pipeline. Essentially, let's say you start your candidate generation starting from, say, you have over 100,000 candidates upstream. You want to apply a subset of models that you can fine-tune this down to 1,000 candidates. To save costs, make it simple. But as you proceed down the line, the model is going to get more complicated. You know more about the user, you know more features. And the features get more expensive, the model get more expensive. You're going to fine-tune this later on until the very end stage. So this naturally forms a funnel, and the funnel have various inputs, multiple models, and you have mixed complexity, right? So I would say authoring this type of pipeline is extremely difficult, and scaling is also very hard. But while we're designing this API, we want to make it easy for users.
Brilliant. And I think one question that really begs is that you showed the directed acyclic graph whereby you actually had the input that was coming in and you were fanning out to two possible preprocessors. And those preprocessors could be anything. They could be something that they're aggregating data, say from a feature store, or they're looking up something in the database. Is it possible, even though this is a direct acyclic graph, is it possible to put circularity in it? I mean, is it possible that I can bind something to the previous node? And if that, what happens? Do we actually detect that there is a circularity in the directed graph?
That's an interesting pattern. I honestly wouldn't say we heavily tested this pattern, but in one of our recent bug bashes, we actually run it and it worked. But we don't think this is This is a particular pattern we highly optimize yet, but if someone have a really strong need for this, we can chat more. But by design, we have a simple example that runs.
But I mean, what you're suggesting is that they can actually have circularity, but the side effects of that we don't know yet.
Yeah, I would say it's less tested. It might be a long tail pattern that is maybe the last 5% of the applications we're going to build.
I think Francis has an interesting question, because I think this definitely would come up when you're actually building these inference graphs and you're building this DirectX cyclic pipelines. How do you deal with versioning? How does the API support level of versioning programmatically? So if I create an inference graph 1 and then I want to go ahead and update that inference graph 2nd, how do you know which version to deploy and when to deploy, and how do you keep track of that? Is there something that we do that generically, or is there something that we have to somehow store that in a meta store or something? Could you talk to
this is a great question. We actually have a lot of discussions around this topic while we're designing the operationalizing story around it. So my personal take on this is I think we should categorize on the frequency and the importance of different types of updates that could happen. So from what we have observed, let's say we deploy an inference graph end to end, you have 10 nodes, right? And what we learned from the industry, the most frequent action that happens is you want to update your model weights. And the model weights is a very simple link to could be some S3 bucket. Then you can assume it's just the same contract, same version that you can update, and you can assume some compatibility guarantee right in place, right? But that covers probably 90% of the actual updates people are going to do. And then proceed with that, you probably want to have reconfiguration. By reconfiguration means for this particular deployment node, I have my graph, maybe I have a dynamic value and say 50-50% chance I do something. Well, other than that, I do the other one. And there's some knobs you can tune that actually does not even need to trigger rolling updates that we can natively support. And by design, each deployment, we can also support updating in place within the same rig cluster. Let's say if you have your interface that you know it is compatible, you can actually trigger rolling updates with your code in place, which means like you can see your graph, and somewhere in the middle of the graph, then you're going to see 2 versions of the replicas spawning in the real time, and the request could be directed to either one of them.
Okay.
Right. So that could happen in the case that if user is confident about the interface is correct and the update is safe, you can locally test and try to deploy this and try to make this update in place. But then it is realistic. But I think realistically it's about industry best practice, because from our discussions, also my personal experience working in maybe larger companies, usually the safest way to do this type of updates is you start a clone at a smaller scale of the new version of the application you want to deploy. You can redirect a very small amount of traffic to it and watch the key metrics and see if you're confident about it. And then increase your traffic load and see if you see any regression. If not, then you can do canary deployment, slowly deploying and redirecting your traffic to the new one. I think this is the safest and recommended way I would suggest user to do. But in the meantime, I'm saying we have all those knobs open that probably cover 90% of the common update needs you have. Reconfigure, update model weights, and do in-place code updates assuming interface is safe, that you're confident that it works.
I think Francis was alluding to the fact that can you actually do what they call versioning pipeline, or can you actually take a snapshot? One last question from Igor before we actually move on, because we have to do the finale and share with the community. Let me read something from Igor. One common problem that they had actually encountered was when creating the model pipeline with serve deployments was tuning and scaling the individual deployments to avoid any pipeline stall. And I think what he meant was probably slow deployments. What I faced most was filling the object store, which means that the object store was spilling into the disk, and consequently spilling was too fast while scaling up was too slow in deployments. Does the new DAG API has any mechanism to prevent pipeline stall? And I think basically is asking that, well, what about if my models are really big, my object store doesn't enough memory, what would happen during the time of deployment? Would I start spilling things to the disk?
I see. I think there are a few parts of the problem. I think one of them is about just disk spilling of object store.
Mhm.
This is generally more on the Ray core or like a Ray runtime level abstraction.
Yeah, yeah.
Right. That's one part of the issue. So, I mean, I think we're making active improvements in this particular area. That's one on the core level. But in the meantime, at SERP level, we noticed previously, if we assume we only have a few deployments running in this Ray Serve cluster, there is not too much we need to do or we can do on the object store level. But now with the deployment graph API bring to the first class API, and there are a lot of optimizations we will plan to do to better make use of shared object store. I can give two examples, and I think Edward also covered it in his presentation earlier. One of them is about, let's say for a image recognition pipeline. The image in here, traditionally, if you just send it through multiple services, you actually need to serialize this again and deserialize it, and the image could be huge, right? And in multi-graph deployment, we actually can avoid making any additional copies and just transfer or use the object directly without the extra cost. So that's one of the observations we spot when, that's why we think Ray Serve is really well suited to solve this type of problem. And the other is particularly for model weights, especially large model weights. And we found this is strong need to build, let's call it a model mesh or model cache management layer that is directly built on top of Ray Plasma Store. Because the attribute of zero copy model loading is very powerful. Like we worked with one community member from IBM, and we showed with correct use of Plasma Store, the cost of hot loading a model is even much lower than running a single inference model. That opens up a lot of new possibilities. And so I think the next item we are very likely looking into, also looking for community engagement and feedback, is how we can better design this model mesh layer that can manage your model weights, either small weights but a lot of models, or a super large model, but it could take a lot of memory in the Plasma Store that actually lead to object spilling, which we try to avoid. So how to properly build this model cache layer on top of Ray Serve is a very interesting optimizations we're looking into.
Well, thanks a lot, Joe. I think Igor actually brought a good point, and I think one of the segues well into the fact that these are the kind of feedbacks we're actually looking for. And so please, take your iPhone, take your Samsung phone, just point the thing to the scan and fill out the survey, because we really want to get this particular feedback going. So I think just to tie things up together to find out, what was the overview about that Ed talked about. What Zhao talked about in terms of scaling the inference pipeline, but then how do you actually operationalize those things? How do you actually put it into production? And that's where Shreyas comes into the next talk to sort of tie things up. And then we'll have the finale demo that actually pretty much illustrates and talks about everything from end to end. So stick around. Shreyas, tell us, what does it mean to operationalize Ray Serve with this new friendly APIs we've been talking about?
Definitely. Thanks so much, Jules. First of all, can you all see the slides?
Yes, we can.
Awesome. All right. Well, hey, everyone. Thanks for tuning in to this presentation about operationalizing Ray Serve, and thanks for sticking with us through this meetup. My name is Shreyas, and I'm a Ray Serve engineer here at AnyScale. This talk is going to discuss how we're making Ray Serve in general more ops friendly and some of the future work that we have planned for Serve. So during the presentation, first, we're going to talk a little bit about the existing workflows that we found that users are using to deploy on Ray Serve. Then we're going to discuss a new ops-friendly workflow that we're developing. And we'll walk through some examples using this new workflow as well as a new Serve CLI. Then we're going to circle back to Zhao's presentation about deployment graphs and show you how you can use this new workflow to deploy your graphs in production. So as you may have seen while working with Ray Serve, this is kind of a classic example of a Serve deployment. We have a class here, myMLModel, that loads a model when it's initialized using some sort of user-configured path. Then whenever it receives an HTTP request, it parses the request and then runs inference on the request's input using that model. Now, as we can see from this code, it's actually pretty simple to convert this model into a Serve deployment, and it's like pretty concise. But Serve also allows you to configure your deployments for production. So in this example, a user can provide a path to their model weights as an init argument to their class, and they can also specify the HTTP endpoint that represents this model, as well as the number of replicas, the maximum concurrent queries, and some resource requirements. Notice that the actual model code is still the same as the previous slide. Only the configuration in the decorator has been changed in this slide. So as Joe mentioned in his talk, ideally you want to be able to define your application logic and your deployment graphs in Python for maximum flexibility. While at the same time you want to put your configuration parameters in some sort of standalone structured configuration file. This gives you maximum flexibility when you're writing your application, but it also has operational advantages as you spend time maintaining your configuration parameters. With this config file, you can provide straightforward version control. You can have ML ops capabilities as well as CLI and REST interfaces. The rest of this talk is going to be about how we get from the mixed config and code on the left to the Python-centric API and centralized config on the right. So let's start by talking a little bit about the processes or workflows that users generally follow to deploy their serve applications to production. This usually starts with developers, data scientists, and ML engineers developing and testing a Ray Serve application locally. After that, a team of ML ops folks deploys the application to production. In some organizations, this is like an entirely separate team, while in others, the same people that develop the app are also the ones that deploy and manage it. Lastly, whenever you need to update your serve application, you usually have the ML ops team write and apply Python update scripts to their live cluster. Now, we've noticed some challenges with this workflow, specifically because you're defining the config in Python. First of all, you don't have a source of truth for the serve configuration running in your cluster. Since each update is applied as a standalone Python script, the true configuration running in the cluster is the result of all of these different scripts combined. Second, the configuration is mixed with the code. This is really challenging if your organization has a standalone ops or platform team, because now they need to navigate and stay up to date with your serve application code in order to understand all the configurations. And last, it's a little hard to build custom ops tooling on top of Serve. Since there's no source of truth and no standalone config, there's no interface that you can use to build tools like custom CI/CD pipelines on top of Serve. So let's take a look at Serve's new ops-friendly workflow. In this workflow, developers still start by developing and testing an app locally. However, now the ML ops folks use a structured standalone configuration file to deploy to production. At this stage, you don't have to wrangle with Python anymore. Whenever you want to apply an update, you can modify the config file and directly redeploy it to your Ray cluster. When we compare these two workflows, the current workflow and the new one, the difference is in the operational loop. In the current workflow, we're using Python scripts to make incremental updates to our serve application. But in the new ops-friendly workflow, we're accumulating all of our config changes into one config file, and we're applying that file directly to the serve application. This new workflow has some operational advantages. First, it centralizes the config. Since the ops team's updates all have to go through the same config file, it's straightforward to track configuration history and roll back or roll forward the state of a serve application. While you can perform this kind of version control on individual Python update scripts, it's a lot more straightforward to track a single individual config file. Ultimately, this file is the single source of truth for the serve application's running configuration. Additionally, by exposing the serve application's configurations in a YAML file, these configurations become easier to access. Instead of digging through a Python application to search for fields like num replicas or max concurrent queries, ops teams can read and write to a YAML config file that stores all these settings in a single place. This file also allows users to build custom ops tooling for Serve. It offers a single unified interface for all of your config settings. It also enables platform teams to build operational tools on top of Serve to better manage and operate Serve deployments. All right, let's take a look at what these config files look like. So these config files are written in YAML format, and they all start with this deployments key. That key contains a list of configurations for each deployment. So the file lets you specify your Serve deployments by writing a deployment name and an import path, as well as any deployment configurations needed for each deployment. For instance, in this example, this deployment's name is hello, and it has 2 replicas. The code definition for the hello function or class can be imported from the file module, which is why its import path is file.hello. Likewise, we have another deployment here, and it's named world, and it serves a maximum of 8 concurrent queries. It can be imported from the file module as well. All the configurations you don't see on this image, like the reactor options, are going to use defaults just like they would if you were working with a serve.deployment decorator. So with this config file, Ray Serve offers the best of both worlds. It can be used by developers and operators alike. And with that, let's briefly take a look at how your serve workloads might be different when you're developing your serve application versus when you're operating it. So during development, you'll probably make a lot of quick updates to your serve deployments because you're trying out lots of different configurations like the init args in order to test out how they affect your deployments. But at this point, you're probably using very few replicas because your goal is to test for the correctness of your application rather than its scalability. Most of your work is going to be done locally using Python as you iterate on your application code. On the other hand, in production, you'll need to operate and manage your deployments. You'll probably have consistent update cycles, and these updates can be used to change model weights or even the application code. At this point, there's going to be a lot of replicas because you need to serve traffic at scale. So most of your work at this point will be using YAML for your config files, as well as the new serve CLI that lets you actually deploy these config files. So let's dive a little deeper into some of these examples to see how Serve offers the best of both worlds and provides a smooth experience in both development and in production. Let's begin with updates. So during development, Serve users usually deploy and iterate their Serve deployments locally. So in this example, we have a user working with the Python interpreter. They've started a Serve application, and they've defined a class called hello, and they've deployed it with the init arg world. Then it looks like they've done some additional work in the interpreter. At the very end, they redeploy the hello deployment that's running locally, and they update it with a new init arg. In this case, that init arg is new world. And now they can test it by making HTTP requests to this updated hello endpoint. Now in production, they would instead usually update a YAML config file and then redeploy it to a Ray cluster. So for instance, in this example, they update their deployment's num replicas to 5. Then they can deploy it using the new CLI command serve deploy config.yaml. This command reads the config file, and then it sends a request to the user's Ray cluster, asking it to update its serve deployments to match the configuration in the file. The ops team can also use a version control system like GitHub to track this config file. If they detect anything unexpected after the update, they can take a previous version of the file and apply it to their Ray cluster using serve deploy. This allows efficient and convenient rollback after updates. Another useful operation is getting live info on your live deployments. During development, you can use the serve.list deployments function to get a list of deployment objects containing the configurations for the deployments. These objects are useful when you're reviewing your configurations and even when you're updating your deployments. Now in production, you can use the new serve config CLI command, which will connect to your Ray cluster and print the YAML configuration for that cluster. You can monitor your deployment's live config using this command. Additionally, you can copy this YAML into a separate YAML file and then edit that configuration. And then you can update your deployments using that file. Another useful tool for you is the serve status CLI command. This command connects to your Ray cluster and then prints the status info for all your running serve deployments. You can use it to monitor your deployment's health and update statuses, especially during production. You can use the included message to debug unhealthy deployments and try to understand what's going on. So this CLI is also really helpful when you're working with the deployment graphs that Jiao talked about. When you're developing your deployment graph, you can use the new serve run CLI command, along with your graph's Python import path to run your entire graph locally. This command will deploy all the deployments in your graph, and then it'll block and print all of their statuses. While this is happening, you can open a separate terminal window and make HTTP requests to your graph to test out your application. Another helpful CLI command is serve build. This command takes an import path to your graph, and then it automatically generates a structured config file for all the deployments in the graph. This is especially useful when you're defining complicated graphs that use for loops or conditionals in your Python code. This command will automatically untangle that syntax and give you a YAML file that can be piped in, and then give you a YAML file that can be deployed to your Ray cluster. That file can then be deployed to your Ray cluster using serve deploy. So everything I've talked about so far is already in progress. In the future, we also plan to use the operational improvements that we've described in this talk as the basis for improved Kubernetes support, A lot of our users run Serve on Kubernetes, and we'd like to make it as easy as possible to deploy, update, and monitor Ray Serve in production. One of our main goals is to improve automated workflows like continuous deployments and continual learning, which many of your users have been asking for. In the future, we also plan to add more integrations with third-party ML ops tools. Ray Serve is a scalable compute layer, and it's really useful for model serving, but we also don't want to reinvent the wheel. We're planning to provide useful features like model monitoring and drift detection, or experiment tracking and model management by adding integrations into Ray Serve with some excellent ML ops tooling. And that brings us to the end of this part of the presentation, but please stick around. We're going to be doing a live demo of all the new features that we talked about today after some Q&A. Before that, I want to take a moment to ask you all to please get in touch with us as we've been talking about throughout this presentation. Be sure to join the community at our Discuss forums at discuss.ray.io. And you can also provide feedback and engage with Ray developers at our GitHub or these Twitter pages. Please also fill out our survey using this QR code to give feedback on the future shape of Ray Serve. And we really look forward to engaging with you more and keeping you updated at the upcoming Ray Summit and over the coming months. With that, let's open it up for Q&A.
Thank you, Shiraz. Wonderful to actually share the friendly APIs. One question that actually popped in my mind, as well as in Nick Hill's mind at the same time, we must be communicating telepathically, but is it possible to do non-disruptive updates of the Ray cluster itself? That is that when you create your structured.config.yaml, and now you go in and say, go ahead and do a Ray serve for that particular DAG, but the DAG is actually running in production and you're trying to update it in live. What happens in the background? Do you actually wait for traffic to stop, or you put it on the staging? What are some of the best practices that you encounter or you envision in using this particular methodology to update live deployments?
Yeah, that's a great question. So we envision a couple of different paths depending on how heavy these updates are. So as Edward and Joe mentioned, one new pattern that we're noticing for machine learning is this idea of continual learning, where you have a model that's continually getting updated and then needs to be deployed. For that kind of an update, we envision a lighter weight path where you don't have to tear down all of your deployments and then redeploy everything. Instead, you can do a lightweight change where you change the path to the model and you're using new model weights when you're running inference. Now, on the other hand, if you have a heavyweight change, meaning that it's very backwards incompatible, it could break things inside of the cluster, then our recommended approach at the moment is to spin up a new Ray cluster, apply your serve deployments on that cluster, which should be a lot simpler now because you have that structured config file that you can apply directly, and then switch traffic over to that cluster. Now, one other thing to keep in mind is that Ray Serve already supports this idea of rolling updates. So already when you update your deployments, you actually don't tear down all your deployments and then start deploying new ones. There's instead this rolling update process where you tear down a couple of the replicas running, you deploy a few replicas of the new version, and then you tear down the rest of the old version and deploy the rest of the new version. So that's still in place with this structured config file and this new MLOps workflow. So you still have the availability provided by that rolling deployment.
Brilliant, brilliant. I think that answers the question quite brilliantly. Another question that you put in your conclusion slide, the magic word Kubernetes. And when people think about Kubernetes, the first thing that pops into people's mind is that can you deep dive a little closely into how does the structured config file interact with the Kubernetes deployment?
Yeah, that's a great question. So the structured config file is really nice because it takes all these configurations that traditionally lived in that serve.deployment decorator, and then it pulls them out and puts them inside of a YAML format where all the configurations are centralized. So now that we have that file, we're trying to think of ways, or we're looking into ways that we can maybe define config files that can be applied to Kubernetes that might embed this information inside of them. So now that we have this native YAML format for serve deployments, we're looking into ways where we can also add native Kubernetes support by integrating that format.
Brilliant. I think that actually answers all the questions. We actually have another half an hour left, and I think this is actually a good time to segue into the end-to-end demo that everybody is actually waiting for, that somehow ties up everything that we talked about from the beginning what the future looks like, the graph APIs, and finally how we actually operationalize those things. So I'm going to hand it over now to Zhao, who's going to give us a demo, and then we'll finally open it up for Q&A for the entire team. And I have my esteemed colleague, a old friend of mine, Paige, who has joined us. So I'll have a couple of questions for her as well. Thanks a lot, Paige, for joining us. So go ahead, Zhao, and go ahead and take over and give us a demo.
Okay, all right. Thank you, Shreyas, for the talk, and Jules for the introduction. And okay, let me double check on one thing, because in this case, I need to swap between slides and code. So can you actually see my screen without any
Yes,
issue?
we can actually do the switch over. Yeah, we loved it.
Okay, now you can see the slides too. And the size and everything look okay? Like it's
Yeah,
great?
the magic works.
Okay, cool. All right, that's good to know. All right, now we have an end-to-end demo for you to cover all the concepts and designs we walked through. And I will walk through the details of this particular demo and see what are we doing on the very high level. So we start taking your inputs. We are building essentially an image classification on content understanding pipeline. And it has a few ingredients in there that shows why graph building API is powerful and how operationalizing API can help to save the day to actually deploy it. So the user input is the image URL. And in this case, I just take a random, let's say, for example, ImageNet image of just a hummingbird just trying to get water or food. And also I pass in the user ID that represents my user side information. And then I will walk through this complex inference graph. At the very end, I want to invoke multiple image models for classification. For example, I want to have a top categorization of this particular image and say we have a very high confidence level knowing this is a hummingbird, and also record which particular version of the model we're dispatching to, which we can walk through more detail in the next slide. And this is essentially the typical ResNet or image classification or fine-tuned product classification model. And the next one we're gonna call into is image segmentation. And you can see this image is slightly cropped and slightly reshaped and transformed a little bit. But essentially, then we are calling another state-of-art computer vision model called mask RCNN, and it will generate a mask that capture the contour and as well as the detected image, detected objects with the responding color into this image. It's very common for like autonomous vehicle or other computer vision models that we try to detect like people walking or trees or buses. And third model we're going to call into is the image caption. And this image caption model is a combination of computer vision and natural language processing, because it's essentially the model architecture with ResNet plus LSTM combined. And what it's going to do is it will try to look at this image and it will try to tell us what this image is about. And for this particular image, the output from the pre-trained model we got is a bird sitting on the table with a frisbee. I wouldn't call the frisbee very accurate, but it's close enough. It's plastic, it's rounded. So that's the best output the model can give us. Cool. And let's dive in a little bit more into details. I'm gonna walk through all the whole thing looks end to end. Then we're gonna incrementally build it step by step using the APIs we introduced earlier. So, and we're gonna start with your input here, just the image to the URL, user ID, and we're gonna pass through a downloader, and the downloader is gonna download the image for you. And then you will pre-process it. By pre-processing means we're gonna transform and reshape it to 224 by 224, which is standard size for ImageNet recognition. And it will also normalize against the RGB channels. And then it will dispatch two models, two particular models in parallel. So one of them is about dynamic dispatch. And in here, we have three instances of the image classifier, all running under the same node. And what that means is we're trying to mimic one use case that we have a lot of classifier in place, but based on the particular image or input we got, we only want to dynamically dispatch to a particular subset of the classification models. And in the meantime, for the same pre-processed image, we want to send it to the image segmentation model, which is pretty what I showed as the mask RCNN. And then I'm going to assign the outputs of those, the featureization, as well as the last FC layer outputs into the image caption. We're going to run the ResNet plus the LSTM, and we will generate the final caption and description of this image. And this entire pipeline at the very end, we're going to render the output end to end, combining all these pieces of information. So now you can see this captures a few attributes of the deployment graph API we walked through earlier. We have a user input, and we have separated responsibility for downloading the image and pre-processing the image. We have parallel calls for the same image being dispatched to two distinct models. We have dynamic dispatch that actually make decision with a business logic or routing logic with respect to user input feature. We have ensembling that those two inputs actually come to the same captioning model as well as the final output. Okay, so that's the end-to-end graph, and let's start building it from the very beginning. So let's start with the first part, and I just get my user input and just want to download image. So in here, I kind of put out some provided inputs already, just to make it simpler to walk through. And I created a data class called content input. You just take two fields, image URL and user ID. It's just a plain Python data class, right? Now, so the very first thing I can do here is I can use the context manager to say this is my user input. And I have a download implementation provided up there already. We have a GitHub link to this entire demo if you want to play around with later on. But for simplicity of a demo, we're not going to dig into the details of each class or function. You can assume the interface is correct. Okay. So now we have a downloader that takes our user input, and as the output, it will be the bytes of this image. Now, I want to see if I'm getting this as correct, as expected, and I'm going to just treat essentially the first downloader as the only node I have in my deck, and I just want to run it standalone. So I'm going to do just stack execute and provide this user input that captures the URL that represents the hummingbird, and let me just print the output here and see what we got. And you can see we started running Zag locally. We started kick off a local rig cluster, and there's a bunch of non-human readable stuff, which is expected because those are just bytes of the image. Okay, now we're done with the first part. We downloaded the image. Now we need to pre-process it, and let's add a preprocessor to it. Now, in order to make this correct, and this is not my root node of the DAG anymore, I just swap it back and say, well, I know how to send the image bytes to the image, to the preprocessor. And given that preprocessing here is a class, so I need to actually instantiate and create an upstream. And I can just say, I instantiate an instance of preprocessor, and the preprocessor takes no arguments in the constructor. So I just create it and use. It has a method called preprocess. And what happens here is I can just send the image byte that downloaded to the preprocessor. I'm calling the cross method preprocess on it. And as a result, for this particular function, I put this image to the read object store. And I want to put it here because I need to fan out the same image to multiple models. And I do not want to make a redundant copy or invoke additional serialization when I don't need to. So the ideal outcome of this is when I run this stack, I should just get an object ref to this particular image. So let's run it again. And this is my local iteration. And you can see, yeah, here's the object ref to this particular image. Now let's revert it back to set the image tensor, and then we can proceed with the next step. We can start creating the dynamic dispatch first. So you can see this is some parent-child relationship here. And if you recall the example I walked through earlier, we have a combiner that takes two models. And this is very similar. We have a dynamic dispatch as an upper parent class that holds references to 3 instances of the image classifier. And you will do some simple dynamic routing, and you will give us an output about which version of the classifier you used. So, and we can create the classifiers here and just say image classification ResNet, and I just create this in the for loop, put it in the list. And I bind it, essentially, I initialize it with a different version to begin with. And then I create my dispatcher. And dispatcher only takes one argument, just a list of the classifiers I want to use. And here's my dispatcher. Now, and we can do a very quick check on the classification output and to see if we are getting what we want to see. Now, the dispatcher essentially has a forward implementation of this class implementation, and it takes the image as well as the user input. We need user input here because remember in here I said my user ID is essentially the key factor to determine which one of the image classifier I dispatch my request into. And I think I take a simple module, like say, like just mod 3 or something. And it will pick one. We don't know which one it is, depending on the user input. So now let's run this again and see what we get. Started running DAG locally, and cool. Now you can see we printed some pre-printed log from ResNet, which is our image classification model, and some printout from PyTorch. We use the PyTorch pre-trained model from Torch Vision. And if we think the classification result of this is high probability, very high probability hummingbird, could be a bucket, maybe a grasshopper, or maybe pencil sharpener, but it's very, very low probability. And the module version that dispatched to corresponds to 1, which is essentially this guy. Actually, the index was off by 1, but it's based on the user ID, we decided to route the request to this classifier. And now let's change this back to the classification output, and let's start adding the segmentation part of it. And in order to use the segmentation model, and I just also need to instantiate it, and this will be a mask RCN model to just add the mask and layering of the image. For simplicity, I'm just not going to show it here, and just let's start to just dive into the image captioning, and we're going to have the output of this render at the very end. So, and now we have two outputs essentially come from calling forward class method that you can also change to a different name if you want to, as long as the signature and the input is correct. Let's pass it to the caption model we have. And the caption model is a combination of ResNet plus LSTM, and it takes no init argument, but at the runtime, it takes the correct input, which in this case, our segmentation output will be fed into the forward function of captioning, as well as the classification output of the captioning. And how about let's make this the exit point of our DAG, and let's run it and see what we get. Supposedly, we should get a description of this image based on the inputs we provide to. Cool. All right. So you can see the output we got here is LSTM is like a sequence model, so you always have a token for start and end. Also have a just like the end of sentence. And it's describing the image as a bird sitting on the table with a frisbee. And this is what this model thinks this picture is about, which I would call mostly correct. And it's very difficult to recognize what this thing is. Okay, now let's put it together end to end. We have the caption output, and let's start combining and actually render this thing in the Jupyter notebook. We have a function called combine, and let's simply put the DAG here. And this will be a new active point that I can try to get a result from, which is just aggregating everything. And I implemented some visualization helper to show us the segmentation results. And VS Code has a pretty nice built-in functionality to just run this thing itself, so we can run it and see what we got. Start running DAG locally. And it's going to go through mask RC. And this is a pretty expensive model, by the way. It takes a while to run. And here's the final output. Now, you can see we aggregated the outputs from all those models with some dynamic dispatch behavior with respect to user input. And the caption thinks this is a bird sitting on a table with a frisbee. And it went through classifier version 1 that we dispatched to the classifier. And the top results of this particular image is we have very high confidence think this is hummingbird. And mask RCN segmentation model is telling us this is what I think the counter of this image should be. You can see this has actually got normalized a little bit into a square, and because ImageNet models were fed into square, we transform in that way. Cool. All right. Now we have walked through everything up to this point for local development. Now I think we can start from local laptop to production deployment. This is the part that Shreyas went through with all the details we want about generating YAML. Now, essentially, we have a little circle here and just to run and iterate, and I show you what could happen here. And you can see it's very easy and quick iteration to get the results you want, right? Now, and we need to add some flavor of serving to it, because now we want to expose this entire DAG as an HTTP to an HTTP endpoint. And now this is where we bring the driver into the picture. And essentially, it's this line. So a DAG driver, we provide a special implementation or default one for you and if you just want convenience, but you are free to implement your own. It's just a simple class deployment if you want to. And there are two things in here. So DAG driver essentially take the DAG and just say, well, I'm here to run this DAG for you, and I'm here to configure HTTP options. And also, you can have a default input schema. And input schema here, I'd say, I can bring my own. We also have a few default ones provided, but if you, in this particular case, if you have a strong need to say, well, I just want to use this particular input adapter, you could do so. And this is our serve entry point. Essentially, you encapsulate and wraps the entire application and expose HTTP to it. Now, the next thing I'm going to do is I will do the serve CLI and serve.run and actually test this HTTP endpoint and see what we got. So the CLI in here is, okay, so essentially, let me clear the screen. Essentially just saying, serve.run. And is the module path, when our file is called deployment graph, so let's do it that way. And the particular DAG with the DAG driver is called serve entry point. So let's run it. Okay, now here you can see a lot of logs printed from Ray Serve because we actually try to deploy this particular deployment graph to a local Ray Serve cluster. And you can see the CLI saying deployed successfully. We're adding a replica each to image classification, 1, 2, and 3, dynamic dispatch, segmentation, and LSTM. Now let's test it with the REST API. So by default, our default DAG driver actually provided the default fast API integration, so which you can pretty conveniently use right here. And, I need to copy this image URL. Let's see, as the user ID is 1. And as I'm invoking it, I can also show the Ray dashboard and say we have those replicas running in the Ray cluster. We have a proxy actor, we have downloader. You can see like the mask RCN get really busy when I'm hitting this request because this is a pretty extensive model to run end to end. And yeah, at the end, we can see the output here. It's a JSON and just saying bird seen on table is a frisbee, ResNet version 1, and classification result pretty much similar as what we have seen locally. Cool. All right, now my local serve cluster development is also done. Now I want to deploy it. And the next step I'm going to do is serve.build. And this is the part about authoring your DAG in Python, iterate locally, test HTTP. You can do all of that. Then serve.build is essentially the one that generates the YAML file for you. And okay, let me code it here, but also make sure I stop the Ray cluster. Okay, so let me do serve.build. I can use the same syntax here, deployment graph. And what is my variable called again? Serve entry point. I want to save it to a YAML file, so I like to say graph.yaml. Okay, I ran into an error because in the actual YAML generation, we found JSON serializable is a pretty valuable contract. Otherwise, you're going to have your inline created class or function that we don't know or do not have full confidence to reconstruct completely. So the fix for this is also pretty simple. Essentially, we want user to use JSON serialized version, like the primitives or import paths of the class or function you want to use, as long as they are defined and visible at top of the file. So the fix for this is essentially, instead of input adapter, I just change this to the path of my input adapter. So this is defined in deployment graph, the input adapter. And I just do the same thing. And this passed. Now, I have generated YAML. Let's take a peek into what the file looks like. Cool. And you can see our DAG looks like this, right? And it has a bunch of like binding. It has multiple instances of classifiers at dispatcher. And you can see that the final generated YAML file essentially captures all the deployments as the backbone of each node in deployment graph used. For example, the first one is we start with the downloading. With the import path of this downloader from the code we use in loader iteration is deployment graph the downloader. That means as long as the runtime environment and your Docker image is set up correctly, we can use this import path to find the body of your downloader class or function. And by default, you use one replica, and by default, I give it to 0.5 CPU. And similarly, you can also see preprocessor instantiated with 1 replica 0.5 CPU. And another point I want to show you here is about a classifier. Remember, we used the same class, but we instantiated multiple times. So like, we need to have an identifier to distinguish those. Otherwise, we're going to run into conflict. We're going to think the name is not unique anymore. And you can see the first ResNet model we generate for classification, we have init the arg of 0 that corresponds to the first value we got from the for loop. And then we have automatically generated the new unique name, knowing this first one was taken to suffix _1, and it was initialized with number of value of 1. Similarly, we also have _2 that has value of 2. Okay, now this is a YAML file, and we want this essentially to be the ground truth of your serve deployment graph application as one YAML file. If you're ops team, ops person, this is only file supposedly you need to know, and it have all the knobs exposed to you they want to know. So let's go to the next step about serve.deploy. And before I do that, I need to start my requester. And serve start. And serve.deploy, and my YAML file is graph.yaml. Cool. And then the CLI will be, we're asynchronously sending a request and say, I want to make this YAML file the ground truth of my current Ray Serve cluster, and please fulfill it. And the controller is busy in the loop and try to do the work for us. And we can see the replica status using the CLI. Those are healthy. Let's see what is happening here on the read dashboard. So we see the download. Let me refresh it again. So you can see the downloader preprocessor populated. And let's stick the API again. So let's play around this user ID a little bit, because in the first one, the ResNet version is 1 because his user ID is 1. So I can hit with the same image, but with slightly different user ID. So the expected outcome here is I suppose still get the same result because I'm still using the same input image, but the ResNet version that it dispatches to essentially means I rather make requests to another classifier model. And for simplicity, I use the same model definition. So they're the same results. Cool. So now we have the serve.deploy. Now this is one common problem that we also tested for HTTP. Now the other thing is we have an issue which could be very common if you have a complex deployment graph end to end. You might find one of those nodes just running really slow, like it could be a bottleneck of your pipeline. If you want to optimize your throughput, but you have one straggler just keep blocking that pipeline, that's not ideal. So here I can show you with this YAML file how simple it is to just scale and change the number of replicas or upscale or downscale a particular node in the deployment. So they're not a bottleneck anymore. And in this downloader, I simply change my number of replicas to 2. And let's say preprocessor, I change it to 2. And before I do that, let's check the dashboard again. So I have only one downloaded instance in my Ray cluster. Why is this showing up? Okay. And I have one preprocessor as well. Okay. But now I changed it to 2. Let me try to redeploy it. And given the API itself is meant to be idempotent, essentially, I don't care what the previous YAML file looked like, but I modified a little bit of it, and I just redeploy a YAML file. This is the new ground truth, and let's fulfill it. And you can see, let's keep an eye on the dashboard, and this dashboard just gonna run, and it's gonna say, oh, okay, I need to make some updates. Let's see what the update should be. Now you can see is we have all the ResNet model populated up again, but now we have 2 downloaded replicas instances running. We also have 2 preprocessors running as well. And just for safety, let's also hit this output again. Let's say I call it this 3, and this whole pipeline is still executable. We might see a different number here upon the new request. Yeah, so this one is actually this time is routed to 0 because we have a model 3 or something in the code implementation. All right, so here I walk you through of everything we did from local graph building. You can see is a full Pythonic local dev experience for quick iteration. And if you incrementally build and play around with your DAG building, that just all the values are fulfilled as if you're writing plain Python code. Then when you want to get to the exposing to HTTP, you can bring your own DAG driver. You can have your own input adapter. And then we get in the CLI for operationalizing how we do serve run and then deploy to a local Ray Serve cluster for another HTTP endpoint validation. How we're going to do serve build to generate YAML, how we deploy it, how we test HTTP, and how we reconfigure the entire application again. So yeah, so here concludes my demo. Thanks for watching. Any questions you have?
Well, thank you, Joe. I was completely mesmerized. This was really magic. I mean, you could do everything in Python right on your visual editor, run everything locally, test everything locally, and then by just creating the YAML structure config file, you can deploy it, update it in real time. This is absolutely brilliant. It's so much different from going into the Python code and changing the number of replicas and the kind of resources you want. You just change the file and then deploy it again. This is what ease of APIs that Shreyas was talking about, and the graph building from locally and then testing it remotely. That was actually brilliant. Thank you very much for the wonderful demo. I think we have about 10 minutes left. I don't know if there are any questions on there, but wanted to thank all of you really for attending. Oh, Paige is here. I had a question for her. I heard that Paige, you're actually doing a webinar in 2 weeks. Something to do with in 2 weeks, something to do with manage Ray Serve. I hope you can beat this demo, because this is now we have set the bar.
Absolutely. And I am dialing in today from the AnyScale offices, watching the great presentations that have happened today. Really excited to see Zhao and Shreyas and Ed's presentations about Serve. And to your point, we're going to be having an exciting seminar series about Serve in the next couple of weeks. So if anybody wants to know how to deploy their first ML model using Serve and do it locally, and as well as host it on AnyScale, you should come and say hi to us in about, when was it? April 27th? April the
27th. I think Sophia just put the link on the chat, and I'll definitely share it with people.
Excellent. Thank you so much. And I just again was completely blown away by the presentations today. They were fantastic, and very much excited to be able to get my hands dirty and do it myself in a couple of weeks. Hope to see everybody there. And yes, thank you.
Well, thank you all. Let me see, do we have hi, may I know when will the Kubernetes Ray integration will be out? I think he's talking about, Guillaume is talking about the KubeRay integration. And does anybody on the team, Simon or Paige or Edward, have an idea when are we actually rolling out KubeRay? I know we are constantly working on it.
So KubeRay, I believe is already kind of available and ready for people to see in the ray-project/KubeRay.
Yes.
Repo,
Yes.
Ready to test out file feature requests, and we're certainly excited to have people test it out. And yeah, that's kind of the path.
Yeah,
we just have a link on the
for a specific serve operator, it will be part of KubeRay moving forward, and we're still in development mode. And like, we're not going to guarantee a time, but we'll be more than happy to basically show any pre-release version and get new tester and trying to get your hands on it.
Yep. Yes, and then you can actually follow the progress on the GitHub.com Ray project/KubeRay, because all the Ray project related are in one particular GitHub, and so any progress you want to find out about KubeRay or find out about Air, it's in there. And so we want to thank Simon, we want to thank Shreyas, we want to thank Zhao for the wonderful magic that you actually showed us. Exactly look like the documentation, exactly look like how you deploy the graph. The APIs were 10 lines of code, and he just showed all the different magic. You didn't have to train a model, you could actually use transfer learning. That was just absolutely brilliant. Oh, by the way, the hummingbird looks like a sharpener that I have. So I mean, there was some probability that you could be a sharpener with the pencil, and so I thought that was rather very cute. And then Shreyas, thanks a lot for the demo, and welcome back, Sophia. I know you had the call. We really like to thank you for coming early from your vacation and then being with us and helping us with all the logistics. So my heartfelt thank to all of you by creating this wonderful communal meetup, and thank you all of you for attending this and staying up late at night. We hope to see you again in a month's time. Hope to see you at the summit as well. So thanks a lot. Cheers, and have a nice pint now.